Okay, we're going to show a couple of different demos here today. We're going to start off with a balloon, and this balloon right here, balloons are insulators, and notice I have a region here that I've actually marked so that we can keep track of it. I'm going to start off by grounding it, by touching it, basically trying to get the charge off. As an insulator, that's a little bit more difficult because it will stay on there and it won't just travel across. Now if I take that section and I actually rub it on what hair I have left, turn that off, and I rub this, and I think we've all seen this where you put it up against the wall or something, right? So as soon as I do, no. So, may or may not stick today. Okay, now the wall is neutral, and yet that's sticking to the wall. Let's show why. We have little pieces of paper here that are neutral, just little pieces of paper, but if I take this over the top of it, it can lift them up. Now why is that? By polarization. Polarization, it actually, the electrons, if you think about, well, if you think about this right here being the nucleus and the electrons are going like this in a circle, well, if I put a massive negative charge above it, they will shift down, making it slightly positive. If I put a positive charge, they will shift up, making it partly negative on that side. Now if I do the same thing with the other side of it that has not been charged, you'll notice no issues. We're not going to get anything from there because I haven't charged that side of the insulator. Taking the same balloon, and if I take water, small stream here, I take the charged balloon, we get, whoa, and we bring the water over because water is a polar molecule. The water is not charged, but the electrons are more attracted to protons than they are, right, than other electrons. Well, oxygen has 8 protons, hydrogen only has 1. So the hydrogen electrons drift closer to the oxygen, making the hydrogens more positive and the oxygen more negative. And so because it's a liquid, it can easily move. So it simply turns over and the hydrogens are attracted to the negative balloon. Easy enough. Well, other things, polarization. This is also showing polarization if we take the electroscope. When we take a negative charge, right now the electroscope is neutral, but I bring this down, a very large negative charge, and notice it's still neutral. I haven't touched it, but the negatives have gone down and the positives are left at the top. I can do the same thing with this, with a positive charge, whether or not I use silk and glass, in which case I'm pulling the electrons up and leaving it positive, still the same charge, or this right here, which is the fun stick, which makes a very large positive charge as well. And if I put the positive and the negative together, I can neutralize it. But as soon as I take away one, the other takes over. Now to show you other things, this right here is called electrophorus. I had someone today actually say this is electrophoresis. Electrophoresis is how we can move DNA molecules and so forth in a fluid. This is not what this is. This is called electrophorus. I'd have an insulator by using the triboelectric series, which is just rubbing by, when you contact things, it just literally transfers electrons. So if I transfer electrons to the plastic, some sort of plastic styrofoam, you can almost hear it crackling a little bit. So now I've added electrons. I take this pie plate, I have an insulator for a handle, and this right here is just magnetic tape from a videotape. When I put it down, the electrons go up, causing these to rise up. It's a little wet today, so if you listen carefully, you can hear a snap. There it was. The electrons were forced from here by a negative charge, forced through the pie plate to my hand because I gave the electrons an escape route. Now the pie plate is no longer neutral, it's positive. And so once again, the little tape raises up. Then I take my hand, I touch it again, and now I've neutralized it. Put it back on the plate. Now again, we've already lost our charge. So we'll do one more time. Try to charge that up. The electrons fly up to the top. It's still neutral. They've just migrated. I touch it. The electrons go to me. It's now positively charged by induction. Induction is the forcing of electric charge. Now let's produce our indicators here using tape. Take off the old ones, and as we're finding out today, everything is disappearing rather quickly. The charge is disappearing very quickly today because it's moist. And if I take 4 pieces of tape, Putting them on the table back here. Can you see that all right still?
Mm-hmm.
Okay, 4 pieces of tape. If you need to stand up and see where you're at, that's fine. I'm putting them a little apart because that way I can get them off the table easily. I'm going to mark the top with a T using a marker. That T stands for top and actually will stand for a positive later on, but we will double check that. We won't simply make that assumption. Take one piece, put here. Just to make it easier, it seems to be easier when I go to the back side. So I'm going to take this other one, do the exact same thing. Notice they both repel each other. We are noticing that they are repelling each other because if you do the exact same process, you should expect the same charge. So if those are positive, we're going to assume these are negative, but we will absolutely test that in a bit. There, we got a nice charge going. So now we have our indicators, but let's find out which one is positive and which one is negative. We'll take our massive negative here, charge it up, attracted, repelled. That's a positive and that's a negative. Before we had the T on there for top, but it turns out the top one becomes positive, the bottom one becomes negative. Well, let's take something else that we know. I'm going to move that negative as far away as possible. I'm going to take silicon glass, repel, attract. Still works. Okay? And our fun stick here, which is positively charged, repel, attract. Well, let's do one more induction demo here. We've got 2 metal balls. Put them side to side. As being metal balls, they are conducting spheres. The electrons, if they're touching, can flow. Now, will all the electrons flow? No, but some of them can. I take a massive negative charge. Charged up. Bring it close, and then electrons from the first sphere will race to this side to get away from this massive negative charge. Well, then, oop, I just touched it. You hear a little snap? Didn't want that. Okay, we're going to have to start over here. Neutralize the spheres. Touch them. Get our massive charge. Get close. Force the electrons this direction. And then trap them. You see how we forced them over here and then we pulled it away once they had migrated. So this over here should be negative. Attract, repel. Well, if this one's negative, then this one should be positive. Repel, attract. That's by induction. We basically push them aside, give them an escape route, and then trap them. Okay, now if we neutralize them, here's the interesting thing most people don't realize. I'm going to neutralize these. Now they're neutral. Watch this. This is actually quite interesting. Nothing until I get close enough, and then it moves close. Over here, it moves close also. Somehow they're attracted to a neutral object like they were with the pieces of paper. Now it's being attracted, watch my hand. Ooh, it's attracted to my hand, as it should be. Anything that I put up there that's neutral will get attracted by polarization. So we have charging by contact, charging by contact, charging by polarization, which will also again cause those to lift up, charging by polarization, and charging by induction, where you force the charge to one direction and then you remove and then you take it away. Thank you.